Good evening from Sydney. I will try to discuss with you some recent developments regarding the development of, let's say, advanced mitigation technologies for the urban environment, also for buildings. Let's say the problem of urban overheating is a very serious problem. A recent study has shown, let's say, that about 13,000 cities around the world are overheating, while since 1980, the number of hours with overheating has been increased by a factor of 3. Actually, there are more than 1.7 billion people which live under very severe overheating. There is a lot of effort during the last, let's say, 15 to 20 years to develop advanced mitigation techniques and mainly advanced technologies for, let's say, mitigation materials to decrease the temperature of cities and to decrease the temperature of cities. I will not present, of course, because I don't have the time, all the recent technologies that have been developed, but I like to go through 3 specific technologies that we work on here in the UNSW in Australia and we have developed. First, I like really to concentrate on the development of thermochromic materials, materials that they change the color as a function of temperature. You see, for example, that these materials can be, let's say, at any color, maybe, let's say, absorbing during the winter period in order to absorb heat and heat, the atmospheric environment and also our buildings. But during the summer period, maybe change the color and be, let's say, reflective or white or any color you may wish, and then back, next winter, maybe also absorbing. These materials have been developed, and you can see, for example, from the testing, that by using these materials, we may decrease the surface temperature compared to, let's say, conventional material up to 21 degrees. You see, for example, the comparative testing between, let's say, a conventional material for, let's say, roofs or pavements, but mainly for roofs, against a thermochromic material. If you don't believe me, you can see the thermal image at the lower part of, let's say, of the graph, and you can see, for example, how much the thermochromic materials can decrease their temperature. However, all these materials are now almost, let's say, commercial. The real evolution and the real, let's say, revolution that has happened during the very last 5 years, it has to do with the development of the so-called photonic materials. But photonic materials are materials that present very high reflectance in the solar radiation, up to 96, 97%. But the real innovation is that these materials may emit, heat, not at every, at the whole infrared spectrum of the atmosphere, but only specific wavelengths in the atmospheric window between 8 to 13 micrometers. So this means that the whole heat, which is, let's say, emitted by the materials, can escape directly, let's say, to the space. In this case, the radiation is not coming back, and in this case, these materials present, very low temperature. So we have developed these materials, and you can see, for example, the testing of these materials during last summer in the Australian desert here in Alice Springs by my, let's say, PhD students. And the results are, let's say, impressive. While the ambient temperature was 44 degrees and solar radiation was about 1000 watts, the surface temperature of these materials was 25 degrees. So we had 15 degrees or up to 20 degrees surface temperature below the ambient temperature without any, let's say, heating and cooling, without any cooling. So we have super cool materials, and this is what we are calling super cool materials, materials that present up to 15 or 20 degrees lower surface temperature compared to the ambient temperature. And these materials can be used really to cool buildings and also the built environment. Actually, we're responsible for the big mitigation projects all around Riyadh in Saudi Arabia, where we're applying this technology in about, let's say, 3,000 large commercial buildings. And based, on the actual simulations we have performed together with Berkeley Laboratory, we expect that we may decrease the ambient temperature in the city of Riyadh up to 4 or 5 degrees, and decrease also the energy consumption of buildings up to, let's say, 35% in Riyadh, where the cooling load is extremely high. What is very important with this type of material is that because of the very high emission and also the very high reflectance, when applied, in climates where we need also heating during the winter time, may cause some overcooling. In this case, we may have, let's say, a very high benefit during the summer period, but we may have a penalty during the winter period. So we have worked and we have developed some new technologies, modulation technologies, which may change the emissivity and the reflectance during the winter time. So these materials, by using, let's say, this modulation technology, may present very high reflectance and very high emittance during, let's say, the summer period, so providing cooling, while during the winter period, in a passive way, may have a very low emittance and a very low reflectance, and in this case may, let's say, provide heating. So we have testing these materials with the modulation in Calcutta, in India, and we have achieved to decrease the ambient temperature during the summer period up to 4.5 degrees. But the most important is that these materials has contributed to increase the temperature during winter up to 2 degrees. So it's a win-win situation, for these materials. We have developed specific technologies and specific materials together with, let's say, some industries, which are commercially available now. For example, Photonic Paints, and you see the results of these Photonic Paints. When these applied, on the on the horizontal, let's say, parts of buildings, we may decrease the surface temperature up to 15 degrees below the ambient one. So it's a natural air conditioning without spending any, let's say, energy. A third technology that I'd like to present you that we have developed, it has to do with the so-called, let's say, fluorescent technologies. Quantum dots, which are really fluorescent materials, very small nanoparticles, have something very specific. Do not absorb heat, or when they absorb heat, immediately they emit as fluorescent radiation. In this case, you don't have any accumulation of heat in the mass of these, let's say, materials, so these materials do not present high temperature. On the contrary, some new materials, the so-called anti-Stokes fluorescent materials, emit more than what they absorb. It looks a bit, strange, but this is what is happening. These materials, they emit more, they lose more than what they absorb. So we have developed fluorescent materials, for the built environment, and we have achieved to decrease the surface temperature of the materials up to 20 to 25 degrees. We have finished all this development and now we commercialize, but because of the very high reflectance of the photonic materials, it is very difficult to be used, in the vertical facade of buildings, very high reflectance, very high, let's say, optical annoyance. So what we are doing now, and we are very close to the end of this, let's say, research activity, we have combined, let's say, photonic materials, but with low reflectance, which means that we have materials of any color, super cool materials of any color, combined with fluorescent materials. So in this case, we compensate the loss of reflectance by using, let's say, more fluorescent, let's say, components. So instead of having a three cooling mechanism, I mean, very high reflectance, very high emittance, very high fluorescence, we have moderate reflectance, any color. You may have a black super cool material that presents, very high emissivity, but at the same time, very high fluorescence. So if you try really to put in one graph the recent developments regarding the, let's say, the cooling materials for the building envelope, let's say 15 years ago, and these are real, let's say, experimental data from the same place, this was really the minimum temperature that we could achieve. And now we are somewhere here. So now we are able really to decrease the surface temperature of the material up to, let's say, 15 to 20 degrees below the ambient temperature. So while, 10 years ago, we were able to decrease the ambient temperature in cities up to 0.51 degree by using, let's say, white reflecting materials or infrared reflecting materials. Now the combined, development of photonic and fluorescent materials really can contribute to decrease the temperature of cities up to 2.53 degrees. We have more than 300 large-scale mitigation projects all around the world that we have achieved to decrease the temperature to 2.5 degrees. And we expect that in the near future, next year, when we will have all the results from, let's say, the project in Riyadh and Kuala Lumpur and Dubai, that we may decrease the peak temperature of cities, real experimental data, up to 4 degrees. For example, in Sydney, that now it is mandatory to use, let's say, cool roofs, we expect that the application of non-very advanced but conventional, let's say, cool roof technologies may decrease the cooling load of the whole city up to 49 degrees. The most important is that these materials may decrease the peak electricity load. You see that the peak electricity load doubles when temperature, goes from 20 to 40 degrees. So we really can decrease the peak electricity demand up to, let's say, 10%, which means 10% lower power plants by using, let's say, these technologies. Also, these technologies can be used, for low-income housing. We have hundreds of applications, thousands of applications here in Australia, but all around the world. And from the experimental, let's say, data we have, in low-income housing without insulation, we may decrease the peak temperature during, let's say, the summer period up to 9 or 10 degrees. So instead of having, let's say, households living at 40 degrees, with such a simple technology, we may decrease the peak temperature up to 10 degrees. However, a recent study that has, let's say, combined all the existing data about, let's say, the impact of high reflecting materials against, heat-related mortality, has found that for every decrease of the albedo of our cities up to 1.1 degree, 0.1, may decrease heat-related mortality by, let's say, 1.8%, which is a tremendous, let's say, impact of, let's say, reflective technologies on health. So I'd like to terminate my presentation by just, let's say, pointing out that during the very last years, we have a tremendous, let's say, research on advanced mitigation technologies for buildings and also for cities. We are able now to decrease the peak temperature of cities up to 4 degrees. We expect to be able to decrease it up to 5 degrees. Perhaps it's not, let's say, enough, but we have a tremendous progress. The development of mitigation and fluorescent technologies, which now are commercially available, may decrease, the energy consumption of buildings up to 40 or 50% without having any air conditioning. May also help to, let's say, keep high comfort standards during the winter period and increase the temperature in, let's say, in heating-dominated climates during the winter period, decreases the peak electricity demand, decreases the energy consumption, decreases heat-related mortality, generates, wealth, and it has a lot of benefits. Thank you very much.